theory. Let A be square n by n matrix. Then the following are equivalent. A is invertible matrix. B. If A is invertible, then by doing row operations we can get identity matrix from it. So A is row equivalent to IN identity matrix. See, in the echelon form, A is going to have n pivotal positions. In an echelon form, A have n pivot positions. D Ax equals to 0 has the only trivial solution. There are no non-trivial homogeneous solutions. E the columns of A are linearly independent if we span column of A, we're going to get the whole Rn whole space. G, the linear transformation vector x going into Ax is 1 to 1 H, the linear transformation vector x going into A times x is surjective onto I exist matrix C such that C times A equals to identity matrix, in this case IN, J, there exist matrix D such that A times D equals to identity matrix on N, emphasize in. Okay, so there are a lot of statements which are equivalent to invertible matrix. In particular, the ones I want to emphasize is A is invertible, coincide that it's a row equivalent to identity matrix. That implies that we're going to have n pivots. Now, A is invertible matrix implies that our corresponding linear transformation x to ax is going to be bijective, which is both one-to-one and surjective, and which also implies that when we're trying to solve ax equals to 0, we're going to have only a trivial solution. And I and j almost kind of the definition of what the invertible matrices are. Determine if matrix A is invertible. We have matrix. We have matrix negative 4, 6, 6 minus 9. For example, we can divide by 3 with second and divide by 2 with first row. So we're going to get negative 2, 3. Dividing by 3, we're going to get 2 and negative 3. Then we do row 2 minus row 1. So we're going to get negative 2, 3, 0, 0. So from here we see that we cannot get pivots in column row 2. And we cannot get pivots in column 2. So it's not going to be a row equivalent to identity matrix. So no, A is not invertible. B, we have a matrix negative 7, 3, 2, 0, 0, 0, 4 minus 9, 1. Now just imagine if we do row operations, no matter what kind of row operations we do, what we're going to do to get is our column of zeros is going to stay as zeros. So those elements, negative 7, 3, 2 and 4 minus 9 might be changed to something, but no matter what we do, we're going to get A1, A2, A3, row of zeros, B1, B2, B3. So there is no way we can get identity matrix. So it's going to be not invertible. Because not row equivalent to I3. That's our first argument. Second possible argument, if you look at the vectors, we have vector column 1, negative 7, 3, 2. We have column 2, 0, 0, 0. We have column 3, 4 minus 9, 1. What you notice is they are not linearly independent. Columns of A are not linearly independent because you can always take 0 of A1, you can take 0 of A3, and you pick any number for A1 vector because it's 0 vector, and you're still going to get 0 vector at the end. So for example, you can pick any k which is not equal to 0. So we got they are not linearly independent, therefore we conclude since columns are not linearly independent, matrix A is not invertible. Same conclusion as we got earlier. So A is not invertible. next matrix which you want to look at, you want to determine if it's invertible or not. If you look, it's already in echelon form, and we clearly see our pivots, and we see that pivot in each row and each column. Therefore, we conclude that eventually we can get identity matrix from it, for example, or we can immediately conclude that A is invertible. Since pivot in each row let A and B be invertible, find inverse of A times B. Okay, so what you notice is you want to take AB and you want to multiply by something. You want to get identity matrix at the end. So the first thing I want to do is I want to take care of that B. So to take care of that B, I'm going to multiply by B inverse. Okay, so B times B inverse identity matrix, you multiply by identity matrix. So we go to A times IN, something which I yet to put, and A times IN is going to be A. I yet to put something here. So now to get rid of A, I need to put A inverse here. And A times A inverse will be I, and that's exactly what we wanted to have. So let me put A inverse in the missing spot. So we wanted to have IN, and that's exactly what we got. We got identity matrix at the end. So formula for A, B inverse is B inverse times A inverse. If we know that A inverse equals to 1573, B inverse equals 9131, find inverse of A times B. According to our previous example, if you want to find inverse of A times B, that equals to B inverse multiplied by A inverse, so which equals 9131 multiplied by 1573. That's now regular matrix multiplication 2 by 2. So we're going to get 9 plus 7, 16. 45 plus 3, 48. 3 plus 7 is 10. 15 plus 3, 18. So we conclude that A, B inverse of a product equals to 16, 48,